It's important because he's our second candidate for the open faculty position we have in advanced reactors. And as a part of his interview, he will make this seminar on the design and optimization of solvent cool fast reactors. So we welcome you here. Dr. Howe was postdoctoral scholar in the Department of Nuclear Engineering at the University of California, Berkeley. He obtained his PhD from Pennsylvania State University and his Master of Science at the University of Michigan, both in nuclear engineering. And before that, he received Bachelor of Science degree in engineering physics from Tsinghua University in China. His research expertise includes design analysis of both light water reactor and not-light water advanced reactor system, multi-physics simulation of nuclear system, sensitivity, uncertainty analysis, modeling, fuel cycle analysis, as well as development, verification, validation, application of next generation reactor physics methods. Please join me in welcoming
Well, thank you so much for the nice introduction. Very glad to be here. I mean, even though I work here, to give you a talk on some of the research project I did in the past few years. There are two parts of this talk. They're both related to the title I put here. Is design and optimization of the sodium-cooled fast reactors. So before I get started, I want to ask you a question, which is the following is the world's first nuclear reactor of any type to generate usable quantity of electricity. So I have four choices here. So, when I was in high school, when you're going to take the entrance exam of the university, I've always been told that if you don't answer, pick C, because most likely it will be C. And yes, so it is actually the experimental reactor, breeder reactor, EBR-1. On December 1951, the electricity coming out from this reactor was able to light up 4 light bulbs. That was the electricity coming that's usable. Now, I see two things from here. The first one is that the idea of the advanced non-light water reactor-based advanced reactors is not something like really new. I mean, there has been this EBR-1, which is a sodium-cooled fast reactor-based technology since 1950s. Okay, and the second way here is that if you define enough or constraints or conditions, everything or everybody can be the world's first. Okay, so actually EBR is the first liquid metal cooled fast reactor, the breeder reactor, and it's designed to demonstrate the Fermi's breeder reactor principle, where he says, okay, we can maximize the usable energy obtainable from the natural uranium. But why do we need that? I thought uranium resource is abundant, so we're told. But in fact, only limited amount of these uraniums can be recovered at a reasonable price, at a reasonable cost. Okay, and our current light water reactor systems can use less than 1% of the uranium that is available in the uranium ore that we dig out of the ground. If we continue to use ones through light water reactors with open fuel cycle, then the current resource can sustain the nuclear industry for like 80 years or so. If we count all the uranium, regardless their grade, then we're talking about less than 300 years. But at the same time, we have a lot of the tailings from the enrichment process we made for the light water reactor fuels. These are called depleted uranium, with enrichment about 0.2 to 0.3% of uranium-235. They're just sitting in the yard of the enrichment plant, and a lot of the energy I see in here are totally wasted. We realized that by using the fast breeder reactor, which has the conversion ratio larger than 1, we can extend the uranium resource by a factor of 60. comparing to light water reactors. The way we do it is that we heat uranium-238 with neutron. And then we transmute the plutonium-239. Okay, after a couple of decades, then we get plutonium-239. Now, if we can do this, we'll be able to extend our resource available to us to about 5,000 years. Okay, but if we can use all this uranium-238 in this depleted uranium, that means that we can reduce the nuclear energy cost, mainly coming from the nuclear fuel, because low-grade ores can be economical again, and we may never need to mine more uranium. Okay, we can just use whatever is already available. Another advantage of using fast reactor is that we can use it to minimize the waste. Okay, I hope you all agree with me that the public hesitation to nuclear energy mainly come from two sides. One is the safety, the other is the waste. Now, talking about the waste, the really nasty ones are these long-lived transuranics, okay, plutonium, americium, for example. And fast system with advanced fuel cycle can be really efficient in destroying this actinides because of the high fission to capture ratio. So I'm showing you here for the light water reactor PWR versus sodium-cooled fast reactor for almost all this actinides. You can see this ratio is much higher in the sodium-cooled fast reactor than in the light water reactors. That means we can reduce, by implementing fast reactors with closer fuel cycle, storage space and decay heat load of fuel repository. And we can reduce waste radiotoxicity faster to the level of natural uranium than otherwise. So right now we have 480,000 metric tons of depleted uranium in the US and about 70,000 metric tons of spent nuclear fuel in the US. Okay, and this number is going to continue to grow. And I see a big problem. And I also see big opportunity. Because for the long term, the fast reactors can give us the solution for the resource extension, which I just mentioned. Also, for the short term, we can deal the waste with the fast reactors. So that's why I break down this talk into two pieces. I want to talk about the two flavors of this fast reactor system. One is more towards the breeder. It's a Bred-and-burn type of reactor, which has conversion ratio larger than 1. The other is the advanced burner reactor, which can help us to minimize the waste, which has the conversion ratio less than 1, just as light water reactors. And one nice thing about the fast reactor system is that these two designs are really interchangeable. They're easy to do. You just change the pitch to diameter ratio in the design, then you can convert a burner to a breeder. You cannot do this so easily with light water reactors. Okay, so I start with the first part, Bred-and-burn type reactor. I'll focus on the design and the performance of a three-dimensional fuel shuffling, which I'll tell you why we need this. Okay, at this moment, recycling is not acceptable in the US for a few reasons. And so we really cannot directly go to the fuel reprocessing. But with fast reactor that is operating in the so-called Bred-and-burn mode of operation, coupled with just open fuel cycle, will be achieve extension of the uranium resource. So what we do is that we breed fissile material of fertile material. We burn a significant fraction of those. And then once we establish the equilibrium state or core, we'll be able to feed with a reactor just the depleted uranium or natural uranium. There's no need for enrichment. This idea, again, is not something new. Has been proposed since 1958. There are two types of the Bred-and-burn reactors. The first one is so-called traveling wave reactor. You probably heard about this from the tire power design. So the concept is really easy. Imagine you have a candle, you light it from one end. Okay, the candle is made of uranium-238. You hit the neutron, you light it up, then you start to have the conversion, then fission. More neutrons coming out, those neutrons will transmute more further materials into fissile, then you continue with the process. So you candle from one end to the other. This is not really economic because the neutrons leaking to the wrong direction will never be able to contribute for the transmutation. So it is more reasonable to design the system so-called stationary wave reactor, SWR. In fact, what's called TWR, traveling wave reactor, by the tire power is actually a stationary wave reactor. Okay. What is done is that instead of having stationary fuel but moving fission wave, we achieve a stationary wave of fission by shuffling the fuel periodically, just as we do with light water reactors every 18 months or every 2 years. We do the maintenance, we shuffle, we reload the core. And again, you have relative stationary fission distribution or fission wave in a reactor. So we're going to talk about the stationary wave reactor in this talk. The physics of Bred-and-burn reactor is significantly different from light water reactors. Remember that in the light water reactors, what is really driving the reactor is the fresh fuel, which has the highest reactivity. So that's why you have, remember the boron let-down curve, right? You have a curve like that of K infinity over as a function of burnup. But if you feed your Bred-and-burn reactor with depleted uranium, which is really low reactivity, you start with some low value. Okay, if you look at this curve, you start with some low value. Then, as you burn the fuel, more further material is converted to fissile. You turn it to be more reactive fuel. Then you see this K infinity increase, and then eventually it becomes less useful, and you'll see this curve decrease. So it's important for us to understand that in order to sustain the Bred-and-burn type of reaction, we really need to burn a fuel to certain burnup. Okay, we're not going to use the fresh fuel because they are kind of useless. And so if we look at this net number of excess neutrons, which is just the neutron balance between the production and the loss. So this is production, right? And then you have a loss from leakage, for example. And we call this neutron balance. We count this as a function of burnup, and we we plot this term as a function of burnup. This is the red curve. What it shows is how productive the fuel is. So at the beginning, you started from 0. The fuel is not producing anything, is not absorbing anything. Then once you start, this fresh fuel is going to absorb neutrons. They're not really giving out any more neutrons. So they're net neutron absorber. And it continues until this turning point. The neutron absorber will become neutron producer. Okay, but this time, this fuel has borrowed a lot of neutrons from the bank, neutron bank, if you will, that is the reactor, but not have really paid back the debt. It is until this moment that this fuel has paid back all the neutron debt and really contribute to the neutron economy, right? So, and if from this moment on, it'll be a neutron producer. And this point here, number 3, is the minimum required burnup for the fuel to achieve. Otherwise, there's no way for you to sustain the Bred-and-burn type of operation. So if we are going to design a Bred-and-burn type of reactor based on just very normal sodium-cooled fast reactor design, like this. You've perhaps seen this type of figure many times, hexagonal fuel assembly design. And our goal is really to improve neutron economy. The reason being, neutrons are so precious because we're going to use them to transmute the fuel. We don't want to lose them, either by absorption or leakage. So we're going to choose a large size of core to reduce the leakage. We're going to use depleted uranium metal as the fuel so that we can maximize the fuel loading. And as a result, we want to lower the power density of the core to reduce the peak fuel temperature. Okay? And we choose HD9 as the cladding or structural material because we know more about their performance in high neutron fluence. Table here shows some basic design parameters, characteristics. But there's a challenge with this design because usually you will see a high peaking at the center of the core in terms of flux or power. Remember, this fuel has to stay in the reactor long enough to be a neutron producer. That means the fuel or the structural material in this elevation will see a lot of irradiation damage coming from the fast spectrum, coming from the fast neutrons. This is a fast spectrum reactor. If you exceed 20% FEMA, that's a unit of burnup. So 20% of the heavy metal has been used. And you're talking about 550 dPa, displacement per atom. That's how much radiation damage that will cause to this field. We only have experience with the HD9 on the level of 200 dPa. Okay, it doesn't mean that the HD9 will not survive beyond that, beyond this damage level, but we just don't know. With the new advanced material development, it suggests that 350 dPa is probably a realistic expectation. So our goal is to really bring down irradiation damage level from 550 to 350. How do we do it? Well, the idea is that if we can minimize the axial peaking of the flux and the power, then we should be able to bring down the radiation level. So the first thought to this is that if we can design a pebble bed reactor where the fuel is continuously flowing, circulating, then we should be able to minimize the radiation damage distribution or profile. But we tried that. It did not work because of many reasons. One of them is that if you have a pebble and the fuel volume fraction in that pebble is kind of limited. So you cannot really produce enough neutrons to contribute to the neutron economy. So we decided that we want to stay with the normal fuel assembly design, but we want to chop the fuel assembly into different pieces in the axial direction. And every time we reload, we shuffle the fuel, we not only relocate the assembly in a different radial location, but also we change their axial location so that with the hope that we can minimize the peaking in the radiation damage level. Well, the issue with this is that, remember in the fast reactor design, there's always a large plenum, either on top or bottom of that fuel rod. Space is necessary to accommodate fission products, fuel swelling, and sodium bond. If we simply chop the fuel rod in this way, then the core regions will be neutronics decoupled because there will be void inside the core. It's going to hurt you in the neutronic performance. This is that we want to remove this large plenum. We wanted to implement direct venting of the fission product into the coolant, the sodium, and we want to use mechanically bonded annular fuel. Direct venting of the fission product is not something crazy. There has been cases, successful cases for this. For example, Pitch Bottom 1, which is a gas-cooled reactor, used directly venting. A neck-cooled reactor in UK has been using direct venting of the fission products before. And for the annular field, our goal is to minimize the axial field swelling by putting a bound between the field and the cladding. And we use the annular field so that we can further minimize the swelling. This type of fuel has been tested in the advanced fuel campaign in this series. So again, this is already have some experimental data backup on the design. So these are the designs that we come up with for the fuel assembly. Shortened assembly, stacked on top of each other. This is also a shuffling machine that can lift the fuel assembly. There are some small designs, gabs, centering buttons, bevels to make sure that the fuel assembly is well aligned in both radial and axial direction. Another close-up at the fuel assembly. This is how the shuffling scheme will, the shuffling machine will work. There is a jaw reaching out and reaching down, and the grip the reinforcing ring. So we redesigned the fuel rod, put it together a new design of a fuel assembly. Then your core now have 4 layers of a fuel assembly, which will facilitate the 3D fuel shuffling. And then we need really to define what are our goals. Our goal is to first minimize the peak radiation damage, but also at the same time, we want to minimize the radial power peaking factor. We also want to minimize the burn-up reactivity swing to reduce the burden on the control rods, etc. So this is the multi-objective optimization problem. And so we design this optimization scheme to find the best shuffling scheme. But I'm going to skip the details in this talk because in the second half, I'll talk more in details. So in the end, let's say magically I got this shuffling scheme coming from the optimization. I'm going to compare what I can achieve with the 3D shuffling with the 2D. The 3D shuffling, here is the shuffling scheme. Core center, core boundary. Fields loaded at boundary as number 1, fresh fuel. Next cycle jumps to this location. And 3 and 4 and start to jump back and forth. Within 12 cycles, after 12 cycles, it's going to be released. 3D shuffling is more complicated. The fuel assembly as a whole is loaded on the periphery. Then the top part is going to this location. And then this location. If you follow that number, the color does not change. Then because of the symmetry of the problem, the bottom one will go to here and then here. The middle ones will follow a different path. But eventually, they'll all be discharged from this location. So now let's compare the performance. With 3D shuffling, what I first noticed is that the peak radiation damage has been brought down to 351. Remember, our goal is 350. We're not there, but really extremely close, comparing especially with the 2D shuffled case. 534, that's 34% decrease. Then we also, if you look at the discharge burn-up, average discharge burn-up, 10% versus 14.5 shows 45% increase in the fuel utilization, much longer fuel cycle in days. So if I compare the shuffling scheme, I do see similarities. Fuel loaded at the boundary, jumping to the center, then back and forth in the inner and outer core. So why does the optimizer tell me to do so? Because it really creates a low radial power peaking at the core center. This is radial power profile, center, and the boundary in 2D and 3D case. They look very similar because that's what the optimizer was trying to do, minimize the power at the center so you can reduce the peaking factor on the radiation damage. But what it really is helping here is the axial power peaking factor, sideway. If you look on sideway, the power peaking factor has been brought down from 2.35 to 2 in the 3D shuffled case. But then the question is, well, if you do that, then your axial leakage probability will increase a lot by 50. If you push the center, then leakage on the top and bottom will increase. But you said at the beginning, we're trying to save as much as possible neutrons because they are really important for the neutron economy. So how does this help? It's kind of counterintuitive. The way it helps can be seen here if I plot the distribution of burnup of the field in the 2D shuffled and 3D shuffled case, again, the side way. Okay? My field is loaded at the outer boundary. Then this fresh field, so they're white. Then as they move in, they start to collect burnup. As they continue to be burned in the field, the color becomes darker and darker. This is where you get discharged, really dark, right? This is a 2D case. You don't really see burnup on the top and bottom of the core because there's neutrons. But if you look at the 3D map, field is loaded here, but then quickly they're moved to the top and bottom of the core where they really sitting next to the high reactivity field, they can receive neutrons and to be transmuted to be more usable field. So that's why we see more red color on the top and the bottom of the core. That is really helping us. And remember, I showed you the red curve at the beginning as a neutron balance. So I'm going to compare the 2D and 3D case. I discretize the assembly into 8 pieces axially. Because of symmetry, I only look at the 4 pieces at the bottom. As they move across the reactor, they pick up burnup. Then we can follow each of this piece to plot the neutron balance or neutron life against the burnup. So if I look at the 2D case, I see the central one, the D, the yellow one, really has to work really hard. It has to reach high burnup so that it can produce more neutrons. For those ones, doesn't want to work. They just sitting there, they didn't really move forward, right? This is the burnup that the red and the green ones reached. But if I look at the 3D case, all of them contribute almost evenly to the neutron economy. So that's why we can bring down radiation level or peak radiation level, because we can even those radiation across the field segments. Another way to look at this is lifetime neutron balance for the 2D. The gray ones really high the center, but for the 3D case, it's much more evenly distributed. Radiation damage level, same thing. Okay, so that's the first part of this talk. I showed you how you design a reactor assembly and the shuffling scheme to facilitate the 3D field shuffling, which really helps to bring down the peak radiation damage level so that we can use that more realistic material bound to facilitate, to actualize the Bred-and-burn type of mode. So now switch to the next project. The multi-criteria core optimization of advanced burner test reactor. This is work we've done together with Argonne National Lab and the Sandia National Lab. The student who did this actually sitting in the audience. And the ABTR is a small-scale advanced burner reactor, which was designed to support the development of the prototype of the advanced burner reactor. And it has a conversion ratio, no surprise, less than 1. It used the fuel made of uranium, transuranics, and zirconium. So this is the code that we use to simulate this reactor. We use the NIMS workbench that integrates all the major software that for the fast reactor simulation. There's a complete process of doing this calculation. The main takeaway here is that it takes about 13 minutes to evaluate one core design, which seems fine, but eventually when we're doing the optimization, it is it's going to be a limiting factor because we'll be looking at thousands of cases just to find the best design. And how do we do the core optimization? First, we need to understand what we need. We define and we refine the optimization. What are the input space? What are the objectives? Second, I choose the right optimization method. Gradient-based or derivative-free, local, or global optimization. Next one, if it's too slow, should I be using some acceleration technique like surrogate model? Next one is how do we choose the final solution? Because these optimizers will give you a set of near optimal solution. It's not going to tell you which one is the best. At the end of the day, it is you who is going to pick the most favorable one and perform the high fidelity calculation on that. So what is our problem? We wanted to design an ABTR that has low reactivity swing. Okay, we want to reduce the burden on the control rods. And we want to minimize the core power, core volume for the cost reason. And also we want to minimize the external plutonium because plutonium is also be feeding the reactor. But at the same time, I want to maximize my peak fast flux because this is a test reactor. I want to have high level of fast flux for the material testing. I can change a few things to achieve this goal. These are my design parameters. I can change the dimension of the fuel rod, how many rods I include in each fuel assembly, even the cycle length, etc. Okay, so identify the input and output. Hopefully, I can, from this relation, I can get, from the relation from input to output, I'll be able to identify my best design. But that's not enough. Because if you look at those optimization objectives, some of them are actually contradicting with each other. For example, if you want to lower the core power, does that mean the flux will be lower? Well, if the flux is lower, how do you achieve the maximization of your peak fast flux? Right? You cannot achieve that one goal without hurting another. So this is where you are. If you have only two objectives, you most likely will end up in the situation that you cannot improving one without hurting the other. And on top of that, we have also a list of constraints that we have to consider. Many of them are peak cladding temperature should not exceed certain level, peak fuel temperature, and sodium void worth, which is the single most important one, feedback mechanism in sodium-cooled fast reactor. So these are the constraints, hard limit. You should never go beyond. And next, we look at our input space. I mentioned the dimension of the fuel assembly. The fuel rods can be changed, but some of them are really continuous. I mean, number of fuel pins probably are integers, but dimension or the radius, for example, radius of the fuel rod, they're continuous. It means that within a certain range, there are infinite ways for you to sample those and to change the design, which is not good. We want to limit the number of choices that we have. So we first discretize those input parameters. We define the maximum and minimum interval and give it a range so we know how many choices we have. So by taking into consideration of all this, we have more than 11 billion possible designs in the input space. I don't think you want to exhaust all these permutations to find the best one. So we really need to have some optimization algorithm to help us. Okay? Then, in order to make this problem even more solvable, we need to see, well, if it's possible to remove some of the objectives. Right now we have 5. Remember, we want to minimize 4. We want to maximize 1. These are the objectives. So I want to see, well, how many of them are really correlated? If they're really strongly correlated, I can remove some of them. So I perform global sensitivity analysis. I tweak the input parameters which are the design parameters, and find the correlations of the output parameters. Okay, this is what we found in the black box. I see that those two parameters, reactivity swing and core volume, are more heavily or strongly correlated with others. So I said, okay, let's temporarily remove those two and simplify our problem just for at the beginning, what we get. So then we picked the optimization method. The one we used in this study is called genetic algorithm. You probably ever heard about it. It's based on the Darwin theory of natural selection. The fittest ones will survive, a better chance to survive, and pass their genetic information to the next generation. So this is what we do. We first choose generate the initial population. Population meaning initial number of designs of the reactor. Then we evaluate their performance or their fitness. This can be done using the code I showed you earlier. Then we pick what we want to keep and we want to create from there. The example to do this is shown on the right. First, we rank their performance. Supposedly, we have those members in one generation. Based on their performance, I rank. So now I have case, you probably can read it, case 5, 3, and 1, the top 3 one. Relative, of course, we have much more than 5. Then we pick those. We directly send those to the next generation. We say, okay, these are the promising ones. And then I marry case 5 and case 3 by picking their attributes of the design. So these are the performance, these are the attributes or design parameters. I pick some from the first case, I pick some from the second case. This is called crossover. Then I randomly change some of the attributes. This is the child, right? And I change some attributes in the child, and I pass it to the next generation. So I have another generation. These ones supposedly work better than the first one. Then I continue to evaluate, to create a new generation until I cannot really improve anymore. So this is the mechanism that helps us with this. The core optimization, the evaluation will be done using ARC. Argonne developed the code. The optimization algorithm will coming from the Dakota code, which is designed or developed by Sandia National Lab. So the first thing we did is that let's stay with the 3 objectives, like core power, external plutonium feed, and peak fast flux. We want to maximize or want to minimize the first 2. We want to maximize the third one. We remove temporarily the reactivity swing. We just put a hard limit, 2,500 PCM, and we remove the core volume. And we do the multi-objective genetic algorithm, MOGA, calculation. The evaluation, again, is done by ARC. In the end, we hope we'll find a bunch of near optimal solutions. So this is how it looks like. The 3 axis here shows the 3 objectives: plutonium feed, core power, and fast flux, peak fast flux. I start my first generation. Okay, as you see more dots coming in, that means more generation is coming, be created, join this design space. And you can see different colors start to show, and this shows more generation is going on. At the beginning, you see a lot of dots in this area, but really this is the direction we're going to, because we're going to minimize the core or plutonium feed. We're going to minimize the core power. We're going to maximize the peak fast flux. So you should be able to see some front. It's called Pareto front, where you can pick your best performing designs. Okay, so after 73 generations, we're able to get this Pareto front. Okay, at the beginning, you see all of dots in this area, but really they're useless because they're not. This is not where the direction that we want. But more and more, you see the dots coming in this line. Okay, And in this whole process, we evaluated more than about 25,000 cases, okay? Because each case takes about 13 minutes. In total, we spent more than 5,000 hours to find the best solution. Okay, so how do the performance look like? This is again the Pareto front formation. I pick any two of them and create a map. I want to reach into these directions. Okay, for example, minimizing the plutonium feed while maximizing the peak fast flux. So this is the direction I'm going. I'm going to pick some design in this location. And the same for the others. This is just a 3D visualization of the Pareto front. So among all these near optimal designs, how do I pick the best ones or the one I need? The different ways. Because you're going to pick along this red curve, Pareto front, it really depends. If you have only two parameters or objectives, and you think R1 is more important than R2, you probably want to minimize R1 more than R2, so you should go this region. If minimizing R2 is more important than minimizing R1, you probably should go to this region. So it means that you can assign different weights to different objectives. You can assign all your weights to one of the objects, or you can evenly distribute the weights. Or you can do something in between, 50 in one and 25 and 25 in the other two. So you have 7 options here. I mean, you have infinite options. We just tried those 7 to see how it have impact on our choice. So these are the performance of these 7 options in addition to the reference case. Well, the reference is the argon design from many years ago. We want to see if our new design can outperform their reference design. If I compare all these numbers in this region, okay, I see, yeah, all this one, we're able to minimize, or let's leave that for a moment, reduce the core power, reduce the core volume, minimize the plutonium feed, and increasing or promoting the fast flux. We achieved our goal. And the one for the reactivity swing, even though some of them are not as good as this one, we're still under the limit, 2,500 PCM. And number 3 and number 6, they are exactly the same design, even though different weights have been applied to the 3. It probably means peak fast flux is really difficult to maximize. So that's why even when you apply different weights, you still end up with the same design. So this is another way to look at the performance. I plot the optimal value versus the reference value. If I'm going to minimize those, I want to see the color dots below the black square, which is reference. If I'm going to maximize them, I want to see them above the black square. And they are, except for this one. But again, 1 in this reactivity swing means it's the bound, upper bound, 2,500 PCM. We're still below it, so we're OK. And again, the issue with this is that it's really slow, more than 5,000 hours till now. We're thinking if we can replace the ARC, which is a physics-based calculation, with some non-physics-based surrogate model. We have different choices here. And also, we want to think if we can even try some hybrid method, combine the surrogate with the direct physics-based calculation. So that's what we tried next. We pick the Gaussian process regression as the surrogate model. I used data sets generated from the ARC calculation to train my surrogate. And then I compare the performance of surrogate versus ARC. This is a relative error of the core performance. Many of them are below 5%. only 2 of them are beyond 10%. Okay, so I consider that acceptable. Then this process takes about 500 hours, training the circuit. Then I use the circuit to do the optimization. Takes about 1,100 hours. In total, we're talking about 1,600 hours, much better than 5,000 hours. Then I'm checking the performance. They look just fine without too much detailed comparison. Except, so what should be below, they're below, what should be above are above. And except for a couple of cases here. They should be below, but they're above. This is plutonium feed. They're higher than the reference. So it means that your reference or your circuit model are not so accurate, which is understandable. What they're buying us is the time. Okay, we understand they won't be as accurate as the directed physics calculation. Next thing I want to see is, can we further improve the effectiveness or reduce the computational time? So we tried this. So this is the first choice, second choice. All right. Next thing I tried is, let's combine the surrogate with the arc calculation. So what we did is that we used arc to generate a smaller sample of points to train the surrogate. Smaller sample means the surrogate won't be as accurate as before, but that's okay. As long as it's in the ballpark, it will help us, and then we'll use this surrogate to do the optimization. Even though it's not as accurate, it helps to reduce the design space as quickly as possible, because I remember the 3D plot with the dots. A lot of the dots in the first few generations are really far away from Pareto front. I know that, and I think we can use the surrogate model to just quickly get away from those dots, move quickly to the Pareto front. And then in the next, after a few iterations, I use arc to generate another set of sample. I use that to improve my circuit model. So that should improve the computational efficiency. So I compared these 3 options here. Apparently, the arc-based optimization is more time-consuming, most time-consuming, but it is most accuracy. The second one is in the middle, but then really, if you look at this, the third option with the surrogate plus the arc calculation, the computational time is really, really short. And part of the reason is because now everything is under the hood of the coda, so there's the data writing and the reading is less time, it takes less time. But still, this sees a lot of improvement on the efficiency. But the cost is, of course, it has a relatively low accuracy. So you have to really make a judgment when it comes to practicality. And this is the comparison of the performance. I have the reference listed here, first option, second, third. And if you look at those, the third option definitely doesn't outperform the first 2. For example, the core power is much higher, and plutonium feed is much higher, slightly improved on the peak fast flux, which is understandable. But if you compare this with a reference, still much, much better in all metrics. Okay. The next thing I want to check is, at the beginning we removed 2 parameters, design objectives, which are reactivity swing and core volume. Now let's put it back. We run arc-based, the most expensive optimization. Let's see how it works. These are the results. In fact, as you compare this column and the 3 objective column, well, this one doesn't really look better than the first one. Okay, the reactivity swing is higher, and the core volume is higher. Okay, so which probably is an indication that we made a good choice at the beginning of removing those 2, because those 2 are really strongly correlated with other 3. You don't really need to consider them in the optimization. So that's how the sensitivity analysis can be really useful to simplify the optimization problem. And this is just summarize the performance comparison, the same plot, okay? But they all satisfy the design objectives. So the second half of the talk really shows you a framework for optimization for the fast reactors. We combine sensitivity analysis with multi-objective optimization method with some acceleration technique based on the surrogate models. It does require a lot of effort to understand how different codes and surrogate model works. It requires a lot of expertise. If you have the luxury of the computational resource, then go with the physics-based calculation. If you want to save time, surrogate model is probably your choice. We plan to extend this method for other reactor types, and we want to continue looking to other optimization methods and other types of surrogate models. With that, I conclude my presentation. I'll take questions if you have. Thank you.
So questions, comments, Jason?
Please.
Did you ever estimate how much extra time it would take to do the 3D refueling as opposed to a traditional refueling?
Yeah, I didn't do a direct comparison, but I realized it could be a problem because you will have much more fuel assemblies. It requires a lot more shuffling time and space. So actually we did, let me see, some study to maximize the complexity of the 3D shuffling. Few things we tried is we tried axially constrained shuffling, which means you take one assembly with 4 segments away, then you put them all at the same radial location instead of putting them in different radial location, but in different axial order. That could simplify your shuffling scheme. Then we consider fewer stacking segments. We reduce from 4 to 3 to even 2, right? And then we consider a larger segment lateral dimension so you can have fewer fuel assemblies with the same core volume. So I can show you something very quickly. When you axially constrain the shuffling, okay, so all the assembly, you see all these numbers are aligned because they are at the same location but different axial or elevation. By doing this, I'm not losing too much. This is my constrained shuffling, and this is my free shuffling 3D. You see only 25 dPa increase, which is not a whole lot, but it saves you a lot of time and space in terms of the shuffling. And I can even reduce to 3 segments, and I see less than 10. So you reduce 25% of your fuel assemblies, but you lose only like 10 dPa in terms of radiation damage. And even with 2. With 2 is not really performing really well, but we also try that.
Other questions?
Yes?
How to install control rods for these 3D assemblies? Because when we are having different power factors, we maybe need to control rods at different positions. If we change the positions of these control rods, the burn-up for these 3 independent assemblies will be different through 3D. And the control rod history cannot be controlled before the cycle. So after one cycle, how do we make sure these burn-up in different assemblies will be ready for shuffling for the next cycle?
Right. Okay. First of all, the calculation done here is called equilibrium cycle. It means that you have run in many cycles and the core performance does not change over cycle. Right? So we know exactly where the radial and axial picking will happen, just as normal 2D shuffle case. Right. So, but in the transition, yes, that's a challenge because from non-3D shuffle to 3D shuffle, the transition is kind of difficult. But once you establish the equilibrium cycle, or equilibrium core, the control is just the same. Thank you very much. Thank you.
Two things. Send me the two presentations.
Okay.
This morning, can you